Okay, hello everyone. Today we will learn about multivariate probability distribution number 3, which contains chapter 5.5 and 5.6, and they are about expected value of function of multivariate random variables and also some useful special theorems. Okay, let's go. Chapter 5.5 is about the expected value of function of random variables. Previously, we have learned about multivariate probability distributions and learned about multivariate probability densities. And the next topic would be um, the random variable related to multivariate um, uh, random variables and their expected value. That would be our next interest. So let's look at the definition 5.9. Let g of y1 to yk be a function of discrete random variables. So here y1 to yk, they are random variables, and those random variables have probability function p of y1 to yk. So this is the p of y1 to yk. This is joint probability function, and then the expected value of um, g of y1 to yk. This is a function of multivariate random variables. The expected value of that is explained in this way for the discrete case. And actually, this is similar extension of the expected value. Here, this is g of y1 to yk. This is random variable, and so this is value for the random variable g of small y1 to small yk. This is value for the random variable, and the next thing is p of y1 to yk. This is the probability density for this value. So actually, this notation, it's the similar extension from the previous lecture that we have learned about the expected value. So g of small y1 to yk, this is value, and the p of y1 to yk, that is corresponding probability for that value. Okay, so this is the expected value, and what if y1 to yk are continuous random variables? If y1 to yk are continuous random variables with joint density function f of y1 to yk, then we can express the expectation this way. Actually, as you can see, this is also a similar extension for the multivariate random variable. It's multiple. We have multiple integrations with respect to dy1 to dyk, and this g y1 to yk. This is the value for small y1 to yk, and f of y1 to yk. This is joint density function. Okay, so with this notation, you can calculate expected value of function of random variables. Let's move on to example 5.15. Let y1 and y2 have joint density given by fy1, y2 is equal to 2y1 for y1 is from 0 to 1 and y2 is from 0 to 1 and 0 elsewhere. Find E of y1, y2. Okay, so from the definition, the E of y1, y2. This is double integration, and y1 is from 0 to 1, y2 is 0 to 1. The interval is simple as this, and we have y1, y2, and we need density 2y1, dy1, dy2. Okay, so let's solve it. So 0 to 1, it is this is 2y1 square y2, and we are integrating with respect to y1, so it is 3 over 2 y1 third y2, and for about y1 is from 0 to 1 dy2, and this is 0 to 1, and if we put y1 equals 1, it is 2 over 3 y2, and if we put 0 on y1, it's 0, so this is it, and this is 1 over 3 y2 squared, and y2 is from 0 to 1, which is 1 over 3. Okay, so expected value of y1, y2 is 1 over 3. Okay. Okay, let's move on to example 5.16. Let y1 and y2 have a joint density given by this, and actually this density function is same as example 5.15, and the problem is different. Find the expected value of y1. So in here we want to find expected value of y1. And actually this is, if we know the density function for y1, let's say f1 y1 is density function for y1, then uh, this is e of y1, and um, minus infinity to infinity, and actually this is from 0 to 1, but we don't know f1 y1 yet, but you can calculate f1 y1 from here. f1 y1 is integrating the joint density with respect to dy2. Y2 is from 0 to 1 to y1. Yeah, yes. This is f1 y1, and actually, if you set g of y1 and y2, this is function of multivariate random variables equals y1, and then you can write this expected value of y1 this way. So e of y1 is double integration and y1 and joint density, which is 2y1 dy1 dy2, and y1 is from 0 to 1, y2 is also 0 to 1, and here, and actually you can change order of dy1 and dy2, and so you can change the order of 0 to 1, 0 to 1, y1 times 2 y1 dy2 and dy1. You can change the order, and interval is same because we are integrating y1 y2. So when the interval is the constant, both of the interval is constant like this, you can freely change the y1 and y2, and from here this y1 is not dependent on y2, so you can write it as this. And actually in here, this one is f1 y1, f1 y1, like this. And so so calculating this way is actually exactly same as the previous way. E of y1, which is the expected value of y1, which is the definition is this one, and actually this is same as this one. So it makes sense, and so let's calculate f1 y1 this is 2, y1, y2, and y2 is from 0 to 1, 2, y1, and so it is from 0 to 1, 2y1, 2y1 squared, dy1, and this is 3 over 2, 3 over 2, y1 third, and y1 is from 0 to 1, which is 2 over 3. And so the E of y1 is 2 over 3. Okay. From here, the important thing is that you check that the previous definition of E of y1, and it is equivalent to the if you use the theorem that you learned previously, this one, they are equivalent. That's the important thing. Okay. And let's move on to example 5.17. In figure 5.6, figure 5.6 is this one, and actually the joint density function is actually the same, which is like this. And in figure 5.6, the mean value of y2 appears to be equal to 0.5. Let us confirm this visual estimate, find E of y2. So from here, y2 is this axis, and what would be the expected value of y2? So the uh, uh, density is like defined is like this, and the expected value, it looks like zero point 0.5. Expected value for y2, it looks like zero point 0.5 is their mean value. That's visually looks convincing, and so let's try to solve it by the equations. So which is e of y2, and is actually we can integrate it um, with double integration y2 and the joint density, which is E of y1 and dy1 dy2. And for y1 and y2, they are from 0 to 1, 0 to 1, and okay, and this is and let's integrate with respect to y1, which is y1 square y2 times y1 square. Y1 is equal to 0 to 1 dy2, and so this is from 0 to 1 1 y2 dy2, and this is 1 over 2 y2 square. Y2 is from 0 to 1, which is 1 over 2 minus 0, and so this is 1 over 2. So we found that E of y2 is 1 over 2. And actually, if you if if you want to find f of f2 y2, the density function, the f2 y2 is actually integrating the joint density with respect to y1 side. So dy1, y1 is from 0 to 1, and here joint density. And if you integrate this with respect to y1, then this is constant function. So um, 2y1, and it's actually 1, and this is so this is if this is y1, then it's uniformly distributed over the interval from 0 to 1. And this is f2y2. So it is natural that the mean of expected value of y2 is 0.5. Okay. And let's solve example 5.18. Let y1 and y2 be random variables with density function. Actually, again, it is same. And this time, find variance of y1. And to find the variance of y1, variance of something is expected value of y1 squared minus expected value of y1 squared. Okay, and we know EY1, so we need to calculate EY1 squared. So E Y1 squared, we want to calculate this one, and since we know the joint density, we can integrate y1 squared to y1 dy1 dy2, and y1 is from 0 to 1, y2 is also from 0 to 1. Okay, and it is actually 2y1 third, and this is from 0 to 1. Integrating it with respect to y1, then it is 4 over 2 over 4 y1 fourth, and y1 is from 0 to 1 dy2, and this is 0 to 1 1 over 2 dy2, and this is 1 over 2y2, it is from 1 to 0, which is 1 over 2. Okay, so expected value of y1 squared is 1 over 2, and so the variance of y1 is 1 over 2 minus, what was ey1? Ey1. And in the previous example, y1 was maybe 2 or 3. And you can check ey1 from the previous example and calculate ey1 square and then solve it for the variance of y1. Okay, let's move on to example 5.19. A process for producing an industrial chemical yields a product containing two types of impurities. For a specified sample from this process, let Y1 denote the proportion of impurities in the sample, and let Y2 denote the proportion of type 1 impurities among all impurities found. Suppose that the joint distribution y1 and y2 can be modeled by the following probability density function. And the problem is find the expected value of the proportion of type 1 impurities in the sample. And here, the y1 is the proportion of impurities in the sample, and y2 denote the proportion of type 1 impurities among impurity found. So, the proportion of type 1 impurities in the sample is that if in the sample the rate of impurity, that's y1, and among impurities, the type 1 impurities, proportion of type 1 impurity is y2. So we want to calculate y1 times y2. That would be the type 1 impurities in the sample. Again, y1 denote the proportion of impurities in the sample. Proportion of impurities in the sample, and Y2 is type 1 impurities among impurities found. So Y1 times Y2 would be type 1 impurities in the sample. So we want to calculate EY1, Y2, and EY1, Y2 is from the previous definition, double integration y1, y2, and the density, which is 2 times 1 minus y1, and dy1, dy2. And y1 is from 0 to 1, y2 is also from 0 to 1. and here this is 2y1 y2 minus 2y1 square y2, and so we are integrating with respect to y1, which is from 0 to 1, y1 y1 squared y2 minus 2 over 3 y1 third y2. Okay, and y1 is from 0 to 1, dy2, which is from 0 to 1. Let's put 1 to y1, which is y2 minus 2 over 3, 2 over 3 y2. Okay, dy2, and this is from 0 to 1. 1 over 3 y2, 1 over 3, this is 1 over 3 y2, and we are integrating it with respect to y2, which is 1 over 6 y2 squared, and from 0 to 1. And so this is 1 over 6. E of y1, y2 is 1 over 6. Okay. Chapter 5.6 is about special theorems. Theorem 5.6 is let C be a constant, then expected value of constant is again constant. And theorem 5.7, let G of y1 and y2 be a function of the random variable y1 and y2. And let C be a constant, then this is true. And actually, we proved similar theorems for the simpler cases. And actually, with you can see that this holds. Um, for example, if for this one, E of C times G of y1 and y2. This C times G of y1 and y2 is again random variable, so you can for continuous variable of random variable y1 and y2, you can specify this as C of G of y1 and y2, and density function of y1 and y2, dy1 dy2, and this constant C is not depend on y1 and y2, so this C can go out, and the if C can go out, then the part the left part is it is C times E of G of y1 and y2. Here actually these are small y1 and small y2, small y1 and small y2, and here they are large y1, g of y1, y2. Okay, so you can prove these theorems. Okay, and here's theorem 5.8. Let y1 and y2 be random variables, and g1 of y1 and y2, g2 of y1 and y2, gk of y1 and y2 are a k number of random variables, and they are functions of y1 and y2, then the expected value of some of those random variables is actually some of expected values of each random variables. And actually, you can also easily prove this theorem using the multivariate probability distribution. So um, uh, you can see that this one is random variable related to y1 and y2, and so uh, let's say y1 and y2, the f of y1 and y2 are joint random joint density for y1 and y2, then the let's say this is 1, and then 1 could be written as double integration of g1 y1 comma y2 plus dot 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 plus gk y1 comma y2 and join random density f of y1 comma y2 and dy1 dy2. And from here, you can write this as a separate integration, like double integration g1 y1 y2 f of y1 y2 dy1 dy2 plus dot 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 plus integration of g of k y1 y2 f of y1 y2 and dy1 dy2, and each of them are e gy1 gy2. So these are expected value of g y1 comma y2 plus dot 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 plus expected value of g k, and this is g1 gk y1 comma y2. Okay, so we can easily prove theorem 5.8, and let's move on to example problems. Okay, let's move on to example 5.20. Refer to example 5.4. The random variable y1 minus y2 denotes the proportional amount of gasoline remaining at the end of the week. Find E of y1 minus y2. Here in the previous example 5.4, y1 was the original gasoline at the starting date, and the y2 is the amount of the gasoline sold. So y1 minus y2 uh, is denote the proportional amount of gasoline remaining at the end of the week. So and we want to find expected value of EY1 minus Y2. And here, in the previous theorem, you can apply the previous theorem, like by using theorem 5.8. Using 5.8, this E of y1 minus y2, you can write it as E of y1 plus E of minus y2. And here, using theorem 5.7, expected value of C times y1 is CEY1. So you this can be written as expected value of y1 minus expected value of y2. Like you can let C equals minus 1, then you can write it as this. So to solve this thing, you can actually calculate EY1 and EY2. So how can we calculate EY1 and EY2? We know the density function, so EY1 is integration y1 times 3y1 and dy1 dy2 dy1 dy2, and here uh, y2 is from 0 to 1, and y1 is from y2 to 1, so y2 to 1. So this is and here this is 3 times y1 squared, and this is from 0 to 1. We are integrating it with respect to y1, which is, well, y1 third, and y1 is from y2 to 1 dy 2. And this is from 0 to 1, 1 minus y2 third dy2. And this is y2 minus 1 over 4 y2 fourth and 0 1, which is 3 over 4. 3 over 4. Okay. That is expected value of y1. And what about ey2? What about ey2? Here, this time from 0 to 1, y2 to 1, y1. This time y2, 3y1 dy1 dy2. Okay, so here let's integrate the inside part with respect to y1, which is 3 over 2 y2 y1 squared from 1 to y2 dy2. And this is we are putting y1 as 1, 3 over 2 y2 minus 3 over 2 y2 third y2 third dy2. Okay, and this is we are integrating it with respect to y2, which is 3 over 4 y4, 3 over 4 y2 2, and minus 3 over 8 y2 4, and from 0 to 1. And so this is 3 over 4 minus 3 over 4 minus 3 over 8, which is 3 over 8. Okay, so using these, ey1 minus ey2 is 3 over 8. 3 over 8. Okay, so yeah, okay, so the answer is 3 over 8. Here is theorem 5.9. Let y1 and y2 be independent random variables and gy1 and hy2 be functions of only y1 and y2 respectively. Then expected value of gy1 and hy2 can be written as e g of y1 times e h of y2. And provided that the expectation exists. And to prove this, it is actually if y1 and y2 are independent, we know that this f of y1 and y2, if they are independent, it can be written as f1 y1 times f2 y2. We learned this in the previously, and for this this is continuous case, and for discrete case, p of y1 comma y2 is actually p of y1 and p1 y1 and p2 y2. We know this from the previous theorem, and by using it we can prove this thing. So let's consider the continuous case, and you will prove for discrete case by yourself. So I will just prove it for the continuous case. So e of g of y1 h of y2. This is by definition double integration g of y1 and h of y2 and fy1 comma y2 dy1 dy2, and this is actually since they are independent, g of y1 h of y2, you can write it as this: f1 y1 f2 y2 and dy1 dy2. And for this one, mm, you can write it as this way. Uh, Here you are integrating with respect to y1, so y2, hy2 and f2y2, they are not dependent. They are not dependent on y1. So this is hy2, f2 y2, and integration g y1 f1 y1 dy1 and dy2. And here, this integration is actually not dependent on y2. This is function of uh, this is not dependent on y2, so this is constant for y2. So this can be go out. So it is integration g of y1 f1 y1 dy1 times integration h of y2 f2 y2 dy2. And here this is expected value of g y1, and this is expected value of h y2. And so this is proof for the theorem 5.9. Okay. Okay, let's move on to example 5.21. Refer to example 5.19. In that example, we found E of y1 and y2 directly by investigating the form of the joint density function given there. We can see that y1 and y2 are independent. And here, this is joint density function, and the interval is constant, like A, B, C, D. They are constant, and this 2 times 1 minus y1, they can be written as, let's say, g of y1 is 1 minus y1, and h of y2 is 2. Then if so f1 fy1 comma y2 fy1 comma y2 can be written as g of y1 and h of y2, and the interval a, b, c, d are constant. Then by the theorem that we previously learned, y1 and y2 are independent. So we can solve this expected value as e y1 times e y2. So here, here expected value of y1 and times y2 can be written as this, and as because y1 and y2 are independent. So the example 5.21, the problem is calculate this one by using this. So from here, we need to calculate e of y1 and e of y2. E of y1, this is double integration of y1, and the density is 2 of 1 minus y1 dy1 dy2, and y2 is from 0 to 1, y1 is also from 0 to 1. And actually, I will leave it to you. You can probably calculate this by yourself. And also e of y2, this is from 0 to 1, then 0 to 1, y2, 2 times 1 minus y1 dy1, dy2, and also I will leave it to you. It will not be very difficult, and so you can calculate this one, and you can calculate this one, and you can calculate e of y1 times y2 by multiplying e of y1 and e of y2. I think you can do this by yourself. And okay. And homework for chapter 5.6 are these. Okay, this is end of the lecture today, and see you next week. Thank you.